So let's revisit this table here, this theorem 3.10, and we talked about all these, right? And we kind of made sense of it with Lagrange notation before. If we derived this one together, and then we basically applied this to all trig functions, right? And so this is the chain rule with trig functions. If you have a function inside of a trig function, then it's basically the derivative of the outer function, and everything's normal except for the fact that we have, a function in there that we keep the same, and then we multiply by the derivative of that inner function, right? So if we're using Leibniz notation like we just saw, it's the same thing except we're going to let u equal whatever that inner function is, right? And then we just take the derivative of the trig function with respect to u, and then multiply by the derivative of that inner function, right? And at the end, we can plug u back in, okay? So that's what, just to kind of go back and make sure that we, just kind of understand that notation now. Now that we've seen it, we can kind of work with that. And you can see it does kind of simplify the derivative of the outer function. It makes it more standard versus having a function inside of there and potentially, that being potentially confusing. So, all right, so let's see a few examples. So here it says, find the derivative of y equals tangent of the quantity of 4x squared minus 3x plus 1. And so, of course, this is going to be our u, right? This inner function here. And so I'm going to let u be 4x squared minus 3x plus 1. And so therefore du dx, or u prime, is going to be 8x minus 3, right? So now I have everything I need. So I'm gonna rewrite this as tangent of u, and then I'm just gonna find dy dx. Well, dy du we could, right? So dy du is gonna be secant squared u, and so then our dy dx is going to be this times this, right? So I'm going to put in secant squared u times 8x minus 3, and then we can just put this value for u back in there, right? And so if we wanted to, we could put this in front. I'll just do that, but either way is fine. And so make sure you just put parentheses around whatever you put inside the trig function. And I made a mistake. It's not this that we're putting in. It's this that we're putting in, right? So it's going to be 4x squared minus 3x plus 1, the original function, right? Not the derivative. So watch out. Don't make that same mistake. All right, and so that's our final answer there for dy dx, or the derivative of this function here, y equals tangent of 4x squared minus 3x plus 1. All right, so last one, checkpoint 3.41. Use Leibniz notation to find the derivative of y equals cosine of x cubed. Make sure your final answer is expressed entirely in terms of the variable x, right? So in other words, like, don't forget to replace u with what it was originally, okay? All right, so let's see. First of all, I want you to, and we'll break this up into pieces, but I'm going to have you do the legwork here. So first of all, what is u? What is our u function here? Good. And yeah, u is the inner function, right? So if you got u equals x cubed, great job. All right. So now let's rewrite y as a function of u. Okay. So y equals, and then write it as a function of u. All right, good. If you put cosine u, that's exactly right. So we just put u in here. All right, so now let's find dy du, and let's find du dx. All right, and I might have said that wrong. So dy du is negative sine of u, and du dx, I think that I might have said I might have said that wrong, but anyway, du dx is 3x squared, right? So now go ahead and use those to find dy dx. All right, and if you got negative sine u times 3x squared, great job. And then now let's do the final step, and let's substitute u, the value for u, back in so we can get it in terms of x, right? So we're going to substitute u back in, and we'll get it back in terms of x. All right, so if you got negative 3x squared, and I just put this 3x squared in the front, right? But if you got negative 3x squared times sine of x cubed, we put x cubed back in for u, right? Then good job. That's exactly right. All right, so that's how to use Leibniz to do the chain rule. And by the way, let me just point out that you can also do this with multiple. If you have functions within functions, you know, if you, like we saw with Lagrange, we can do if we have f of g of h of x, then it's just going to be f prime, the outer function, with everything inside the same, times g prime with everything inside the same, times h prime, right? And so you can do the same thing with Leibniz, where you could have dy dx equals dy du, right? And then you could have an inner function inside of u, so it could be like du dv, and then you could have dv dx. Oops, not equals, but should be multiplied there. And then dv dx. So you could have something like that too. So it's really the same thing. You just multiply the derivative of the outer times the derivative of the next most outer, and then until you get to the most inner function, the derivative of the most inner function. All right.